Welcome back. Today I'm going to be talking about TMV, replication, and translation. So first of all, some background and basic information of TMV, or the tobacco mosaic virus. It's a single-stranded RNA virus of filamentous morphology, so it's an RNA filament. It is made of 2,130 molecules of coat protein, so that surrounds the RNA to keep it from interacting and keep it safe, basically, until it needs to replicate. It is 6,400 bases long, which is reasonably short. It can only make 4 proteins from its one single piece of RNA, and the size is from 300 nanometers and a diameter of length and a diameter of 18 nanometers. This is a standard size, and it's so specific that you can even use it to calibrate microscopes. Every single TMV is the same length and diameter. So the problem is a replication of the TMV virus. So as you already know, the TMV, tobacco mosaic virus, is one strand of RNA, but it needs to make 4 proteins for it to function. So how is this possible when the RNA can't allow for reassociation of it to be able to be translated? So TMV is able to make 4 proteins with only one RNA, and I'm going to explore how this is possible. So TMV replicates and translates. So there are 2 ways to get around these problems we've talked about. The first is, as you can see here, where it says read through, is a leaky stop codon, which normally will stop once the translation hits the 126K, which is the molecular weight of this polymerase that's producing to be the protein. However, 10% of the time, it's able to leak through to complete and make the 183K, which again is just the molecular weight polymerase to be made, which means it's allowed to continue to translate through. Instead of just making the 128K, it's able to go all the way through and create the 183K. This is how it makes 2 of the 4 proteins. So these 2 are the polymerase, and then it still needs to make the movement protein and the coat protein. However, there's a stop codon at the end of the 183, so it's unable to leak through to create the 30K and the 17K, 17.5K, because they're separate. They need to make separate proteins. They can't just be using what's already been made. And as we've already talked about, they can't. The replicase can't jump back in to create these proteins, so it wouldn't be able to make the 30K and the 17.5K. So move this. The second way it replicates and translates. So this is how it makes the 30K and the 17.5K. So replicase binds to the 3' end right here of the positive sense RNA. It then copies itself back to the negative sense RNA and creates a mirror image. So here we can see, if it was this way around, the original strand is the 4 first codon, the first 4 first bases are GGG. It'd now be CCC. So now a mirror image. It can be used as a template, create more original sequences. So here you go, is a positive strand, a positive sense strand of the RNA, which is now translated back to GGG. Now here you can see these little stars. This is where, on the template, replicase is allowed to jump back in. So it can, when it tries to make back the original strand, it can make sections of it. So here you can see that this section had just been made here to make this one protein, which is the, I think, 17.5K, and this whole thing has just been made. Instead of the whole strand being replicated, it can section it out, and then these sections can be translated, as you can see here. Thank you very much for listening.